So let's look at the second way to do that projection, and that is we have our couple cluster Schrödinger equation, and here acting hard to Fock was our couple cluster energy, and the couple cluster wave function, which is e to the t acting on hard to Fock. And then, I mean, this is an equation, and I'm allowed to do everything with that equation as long as I do it on both sides. So what I do now is I pre-multiply the whole equation with e to the minus t from the left. So I look at this equation, so I get e to the minus t h, e to the t. And then e to the minus t, that's an operator, that's a number, so I definitely can move that past that number. And then I get e to the minus t, e to the t, hard to Fock, and that is then e couple cluster phi hard to Fock. Well, this is one. You have to be careful with all those operators. Careful in the way, don't assume that they commute. In particular here. I mean, if they would commute, then I just could move the e to the minus t past the h, and I would have h hard to Fock. But they don't commute. So you can't assume that. This, by the way, this sort of triple is, at least in one version, shows up very often in all kinds of couple cluster theory. And that is sort of, this is called a similarity transformed Hamiltonian. Formed Hamiltonian. Now, in order to get the energy now, I do as before. I project this equation now against my hard to Fock, which is sort of our reference state. So I get phi hard to Fock, e to the minus t, h e to the t, phi hard to Fock, and now you can say immediately I get that this is my couple cluster energy. Now let's get a bit more specific now and really evaluate this thing. And if you don't mind, I move the couple cluster energy to the left, so I can keep on writing to the right. Now what I have to do now, I have to insert the expansion of the operators now. So I have my phi hard to Fock, and I have to the e to the minus t. Now that's now the expansion of not e to the x, but e to the minus x. And that goes like 1 minus t plus 1/2 t squared, and so forth. And then just keep the linear term right now, but expand it in t1, t2, and so forth. So this gives me t1 minus t2, and so forth. Then I have my Hamiltonian. And what I have e to the t hard to Fock. Now, as we discussed before, those since I don't know what sort of they're going to do to the Hamiltonian and let them act to the right, I have to let them act to the left. And we discussed before, if an excitation operator acts to the left, that is the adjoint of the excitation operator acting on this, and that's a de-excitation. And de-excitation means I want to replace in this determinant all the virtual orbitals by occupied orbitals. But there are no virtual orbitals because this is the hard to Fock. So all those, they actually can't do anything to that hard to Fock. Well, they make zero out of it. So I'm back to my original one, which means I'm back to this one. Which basically means for the calculation of the energy, this is sort of superfluous. I mean, you don't need to do that at all. Why we do that and why then, for consistency reasons, you also write it up here, comes when we want to calculate the amplitudes. There it really makes a difference.